In this session, let us derive the pressure difference across a liquid surface. Okay, I will be considering a liquid surface, and from that surface, let me take an element now here, right? Okay, let us take a curvilinear rectangular element. Okay, let me take like this here. So this is the curvilinear rectangular element. Let me consider like this now here, right? So this is curvilinear rectangle. Okay, let me take a rectangle. It is like a rectangle, but it is curvilinear, not rectilinear. It is a curvilinear like this. Okay, so this is a curvilinear rectangular surface, right? Rectangular element of the surface now here, right? Okay, now let me take this as A, B, and let me take it as C, and this is take it as D, right? Okay, this is the this is curvilinear. Okay, curvilinear element ABCD of a surface of the liquid, right? Okay, now if I am considering this curvilinear surface now here, right? For example, if I am considering the center of curvature is this side now here, so let me consider like this now here. This is the radius of curvature of this surface, that is AB. Let me take it as R1, right? Afterwards we'll be learning about this now here. First let me complete this. If I am taking BC, if I am taking the radius of curvature of this curve, right, it might not be in the same position, so let me take it as R2. If both are spherical, we can take it as R1 equal to R2. Until then, let me go with in general, right? So R1 is greater than R2. Let me take like this, and let me take this as point O, and let me take it as this as point O dash. So what I have taken? I have taken a rectilinear, right, element of the surface. Okay, let me write what I have considered here. Okay, consider a curvilinear. Okay, sorry, it is curvilinear element. So what is the curvilinear element? Curvilinear element ABCD. Okay, consider a curvilinear rectangular element. Let me make like this again. Curvilinear rectangular element. So what is that curvilinear rectangular element? That is ABCD, right? Of the liquid surface. See what we are doing? We are deriving the pressure difference across a liquid surface. From that liquid surface, I have considered an element ABCD, curvilinear rectangular element ABCD of the liquid surface. Then what I will be doing? What I will be doing here is I will be applying a pressure at the concave side. Okay, if I am taking, this is a curvilinear, this is a convex, and this is concave. Right? Okay, let me apply the pressure because we are finding the pressure difference, right? So when excess pressure is applied on which side? Concave side. Okay, which is the concave side here? Just think here, this is the concave side. I am applying an excess pressure. If I apply the excess pressure, this ABCD will take new position. If I apply pressure, it will go upside now, right? Okay, what is that position? Let me take with different color chalks now here, right? Okay, let me consider this ABCD here. When I apply pressure on the concave side, this ABCD will take a new position. So what is that new position? Let me consider like this. So this is the new position of ABCD when I apply the pressure now here, right? Okay, this is the new position when I apply the excess pressure now here, right? So let me take like this. Okay, so which is this? Let me take it as A dash, B dash, let me take it as C dash, and let me take it as D dash, right? Okay, see, when excess pressure is applied on concave side, the new position of the element, the new position of the curvilinear rectangular element is A dash, B dash, C dash, D dash. Okay, see here? I have considered a curvilinear element ABCD of the liquid surface when I apply the excess pressure, right? Okay, when the excess pressure, how much pressure did I apply? Let me take it as capital letter P. When excess pressure is applied on the concave side, the new position of the element is A dash, B dash, C dash, and D dash. Okay, let me take what are these and let me go ahead now here. In this, let me consider here the length of AB, let me consider like this. AB, let me take it as X. Okay, how much is AB now here? Let me take it as X. If I apply the pressure, the area will increase, right? So if this is X, what is A dash B dash? Shall I say like this? A dash B dash is X plus dx, because there will be increase in this, right? Increase the area, right? If I apply the pressure, the area increases. So if I am taking the length of AB, the length of the AB, let me take it as X. So what is the length of A dash B dash? The length of A dash B dash is X plus small increase, that is dx. Okay, now let me take this BC. Okay, let me consider BC. What shall I consider BC as? What? If BC is Y, what is B dash C dash? Let me write B dash C dash. That is Y plus little increase. So what is that little increase right here? dy. Okay, what is this? B dash C dash? That is Y plus dy. And this is X, let me take it as Y, and this is, let me take it as Z. So what is this B dash? Let me write about this. B dash. So what is B dash? Means it will be increase in this direction, upward direction. The upward direction, it is also small. Let me take it as dz. Do you understand? See, what is B dash? That is increase. So how much is increase? Small increase. Let me take it as dz. Okay, once again, AB is X and this is X plus dx. This is Y. What is this? Y plus dy. And if I am considering what is this? This is dz. Right? Since the diagram becomes clumsy, let me not write these all things. I written there here, right? Okay. Let me understand much more about this here. Just understand here, right? So this increase in the upward direction, let me take it as B dash as dz. Okay. Now, knowing what all this, let us go ahead with the derivation here, right? So this is just an introduction about what I have taken here. I have just taken a curvilinear rectangular element and I applied pressure, and when I apply the pressure, it will take a new position, right? So that is A dash, B dash, C dash and D dash. Okay. Now, let us go ahead with the deduction. Now, let me, after knowing what are this, let us calculate what is the area ABCD. Okay. First of all, come on, tell me now here, what is area ABCD? Okay. This is ABCD. I told you it is rectangular. So what is the area ABCD? What is AB? X. What is BC? Y. So what is the area now here? That is X into Y. Right? What is area ABCD? Area ABCD is X into Y. Length into breadth. Right? Okay. Now, after knowing what is ABCD, let me take what is the area A dash, B dash, C dash, D dash. Okay, do you understand? This area, I am calculating the bigger area now here. A dash, B dash, C dash and D dash. So what is that? You know, what is A dash, B dash? It is X plus dx. This is what? Y plus dy. Shall I multiply here, right? So as I multiplied X and Y, I will be multiplying these two. What is A dash, B dash? Let me take like this. X plus dx and Y plus dy. Length into breadth, right? Okay, now let me multiply this. What do I get here? This is X, Y plus X, dy plus Y dx plus dx dy. Okay, just I multiplied X dy, Y dx, dx dy. Do remember, these are very small, dx and dy. As dx and dy are small, as this is a small quantity, this can be neglected. Right? So this can be neglected. If I neglect that, what do I get? Xy plus X dy plus Y dx. Okay. Now, after knowing the area ABCD and A dash, B dash, C dash, let us think what is the increase in area. Okay. Now, let us consider what is increase in area. Okay. Increase in area. So, how much is the increase in area? Okay, this minus this, right? So if I subtract this from this, I will be getting what is the increase in area. Okay, so what is this now here? Xy plus X dy plus Y dx. I written this minus, what is this? Area of ABCD. What the area of ABCD is? Xy. right? I'm calculating what is the increase in area because I want a surface energy. We know what surface energy. When we speak about surface energy, there will be increase in the area. That is the reason why I consider increase in area. Okay, what do I get now here? Again, xy will get cancelled, right? So if I get cancelled, what do I get? X dy plus y dx. So what is this thing here? This is increase in area. Do you remember? This I have not considered. Why I have not considered? Because small quantity multiplied by small quantity, we will get much more small quantity, right? So if you multiply half with half, we will be getting 1 by 4th, right? That is the reason why we are neglecting this, because both are small quantity and multiplication of small quantity is even more smaller quantity. If I neglect that, I will be getting with x dy plus y dx. That is increase in area. Now, I will be discussing about what is the increase in surface energy. Let me calculate. What is the increase in surface energy? Okay, let me take increase in area. Let me take it as delta A. Shall I take like this? Okay, increase in area. Let me take it as delta A. This much. What is the increase in surface energy? So, what is increase in surface energy? Let me take my here. We know what is the formula for surface tension. The formula for surface tension is surface energy divided by what do I get now here? Area. Increase in area. So, what is surface energy equal to? Increase in surface energy equal to tension, right? So that is surface tension into area. So how much is increase in area? Let me call it as delta A. Do you remember? We know we have this formula, surface tension equal to surface energy divided by increase in area. So what is increase in surface area? Tension into increase in surface area, right? So that is equal to, shall I tell you this? This is tension. What is in increase in surface area? X dy plus y dx. Okay, do you understand? Increase in surface area is surface tension into increase in area. So surface tension increase in area is this much. This is increase in surface area, energy. You know what is going to be energy? There is nothing but work done. Okay, now I'll be equating this with the work done. So do you understand here what we are doing in this derivation? Next, I'll be going with the increase in surface area. We got this much. Let us go ahead with work done. We know how much is the work done. Work done can be equated with the increase in surface area. Increase in surface area. We know that surface energy is nothing but work done to increase the surface area. That is the reason we can say that work done can be equated with the increase in surface area. Okay, that is equal to, what is work done? What is the formula for work done? Force into displacement. Okay, so what is the force? Let me take F is the force. So what is the displacement? Displacement is this much, right? So this is how it displaced. So what is displacement? dB dash. So how much is dB dash? I have taken dB dash as dz. So that is the reason I'll be taking it as dz. So what is this? Work done is force into displacement. And what is it's an increase in surface area? Let me take it as P. And what do I get? X dy plus y. What do I get now here? Dx. X dy plus y dx. Now, let us go ahead now here, right? I got this and I have multiplied. I got what is the work done? F dx. Okay, next, we can write force in terms of pressure now here, right? We know what is the formula for pressure? Pressure is equal to force divided by area. Now, let me write force in terms of pressure. What is the pressure? What is the formula of force in terms of pressure? That is pressure into area. So let me take it as pressure P. And what is the area? Which was the earlier area? That is x into y, right? So let me take this area as x into y. And what do I get now here? dz. So that is equal to, let me write T x dy plus y dx. Now, let me find what is the expression for P now here, right? P is equal to, let me write T here. Right? Okay, let me bring this xy to denominator. If I take x, y, x will get cancelled. What do I get now here? 1 by y dy plus, if I bring xy to here, xy, y will get cancelled. What do I get now here? 1 by x. So what is 1 by x? 1 by x into, what do I get now here? Dx. And let me take it as question number 1. Right? So do you understand what I have done? Work done to increase the surface area, right? So I have equated, I got with the expression for P is equal to T 1 by y dy plus 1 by x dx. Now, My next intention is what is the value of this 1 by y dy and 1 by x dx. What is that? Let us calculate. Okay, I will be using a triangle here. Okay, let me consider a triangle ABO and another one triangle. Let me consider it as A dash B dash O. Let me consider these two triangles and calculate what are the values of these two. Right? Okay, let me consider. Since, so let me take first triangle. What is the triangle what I am considering here? ABO. This is the triangle here, right? So since triangle ABO and triangle ABO and another triangle is here, see here, A dash B dash O, right? So this is also triangular here, right? So that is A dash B dash O. Okay. If I am considering ABO and A dash B dash O, if I am considering like this, since these two triangles are what we say here, similar, right? They are similar triangles. If two triangles are similar, we know the ratio of corresponding sides are equal here, right? Okay, let me take the ratio of corresponding sides. Okay, first of all, let me take A dash B dash. So let's take like this, A dash B dash. What is the corresponding side of A dash B dash? Corresponding side is AB. Let me take it as AB. That is equal to, what is the corresponding side of A dash O? The corresponding side of A dash O is AO. So let me take it as A dash O divided by, see here, A dash O divided by AO. Let me take it as A dash O divided by AO. Okay, let me write. What is this? A dash B dash, that is x plus dx. Shall I write like this? X plus dx divided by, what is AB? AB is x. We know this, right? Now, let me write. That is equal to, what is A dash O, man? Where is A dash O? A dash O is this much. How much is this? We know AB is R1. And what is this distance? This distance is nothing but this distance, right? We have considered this distance as what now here? dz. So what is A dash? A dash is dz. Okay, where shall I write now here? A dash O is R1 plus this. This is R1 plus this. How much is this now here? That is nothing but this. So shall I take like this? R1 plus dz. Right? Why dz? Because this distance is equal to this distance. Right? Okay. A dash O divided by AO. What is AO now here? That is R1. Let me consider it as R1. Right? Okay. Let me go ahead now here. Right? If I am calculating this, what do I get now here? Right? If I am calculating here, let me take here. Okay. Let me take like this. X will get cancelled. Let me write 1 plus, what do I get? Dx by x. Shall I like this? 1 plus dx by x. That is equal to, what do I get? R1 again, we'll be getting it 1 plus dz divided by, what do I get now here? This is R1, right? So dz divided by R1. So again, this 1 will get cancelled. What do I get here? That is dx by x is equal to, dx by x is equal to dz divided by, what do I get now here? R1. Now let us understand what do we need now here, right? So we need 1 by x dx. Okay, shall I get here? 1 by x dx. Okay, we got that now, right? So what is 1 by x dx? This value I calculated. What is 1 by x dx? 1 by x dx is how much now here? dz divided by R1. dz divided by R1. So let me take it as equation number 2. Okay, see here. This much I calculated and I got what is the value of this value. What is the value of this now here? dz divided by R1. Similarly, if I take this side triangles, right? Triangle BCO dash and another one is B.Sc O dash. If I take that, what do I get now here, right? Okay, let me remove this so that I can extend the derivation here, right? Okay, now if I get similarly, I will not be solving similarly, you can write like this. Similarly, when I am taking 1 by y dy, I want this now, right? Instead of writing 1 by x dx, I will tell 1 by y dy. That is equal to, shall I write? dz divided by R2, radius of curvature of the second wave, right? So here R1 we got, here this is R2. This, shall I take it as equation number 3? What I will do now here, right? I will be substituting these two into that now, right? Substituting, see here, substituting equations 3 and 4. Okay, in what we get now here? 1. Substituting 3 and 4. Sorry, it's not 3 and 4, it's 2 and 3, right? So 2 and 3 in 1. Okay, if I substitute, what do I get? P is equal to T. Okay, P is equal to T. 1 by y dy. Where is 1 by y dy? 1 by y dy is how much now here? dz divided by R2, right? Okay, there is plus, here there is a plus. Let me take like this. 1 by x dx. How much is 1 by x dx? dz divided by R1. dz divided by, what do I get now here? R1. So let us understand about this now, right? So T is equal to P is equal to T dz divided by R1. Okay. This is about the derivation. I substituted here 1 by y dy, right? So instead of writing that, I consider it as dz. So P is equal to T dz divided by R2 plus dz divided by R1. So this is the pressure now here, right? So when I consider about this pressure now here, so here I have made a little bit mistake here. I have not considered this dz at all, right? Okay, let me take that. If I am considering this dz, if I take dz here, so it will become dy divided by dz. I have not considered here dz, right? Okay, let me take dz here also. It will become dz here, right? Okay. Now in the similar manner, I can do here also, right? So here dz, let me take here also itself. That is dz. So what do I get? 1 by R1. Let me do the same thing. I have forgot to take that dz. Let me take this side. So what do I get now here? 1 by R2. So now, what is 1 by x dx by dz? That is 1 by R1. Okay, let me take like this. So this is 1 by R1 plus 1 divided by R2, and this is the expression. Okay, this is the expression for pressure across a liquid surface. What is the pressure across the liquid surface? P is equal to T 1 by R1 plus 1 by R2. Right. So do remember, this is the derivation, and this is a 5 marks derivation which can be asked in the examination, right? Derive the expression for excess pressure across a curved surface. Now, so do remember this formula. P is equal to T 1 by R1 plus 1 divided by R2. Now, let us take some more cases here in this. Okay. Now, if I am considering different cases, what do I get? So do remember, this is an important derivation. Now, let us go with the different cases here. Now, let us write with the different cases. Okay, let me go with the case number 1. Right, case number 1 says that when AB, okay, I think you remember this. Okay, see here, this is AB and this is AC and this is a curvilinear, right? This is AB and this is what now here? BC. The center of curvature is this side and the center of curvature is this side. Okay, if the center of curvatures are on the same side, we got this now, right? When center of curvatures, okay, when center of curvatures of AB and BC are in opposite side, here center of curvatures are in the same side. So if they are in same side, this formula holds good. If they are in opposite sides, right, if this center of curvature is of one is here and another one is there, if they are in the opposite side, then what will happens to the pressure that we will be learning, right? If it is in the opposite side, the pressure formula will be like this: T 1 by R1 difference of 1 by R2 instead of plus, right? If it is plus, so understood that center of curvature is on the same side. If center of curvatures are in the different side, so we'll be considering instead of plus, we'll be taking it as difference, right? Okay, this is the first case. Now, let me take case number 2. When surface of liquid, okay, see, when surface of liquid has two free surfaces, okay, surface of liquid has two free surfaces. Do remember, when surface of liquid has two free surfaces means, do remember, it is an example of what we say here, soap bubble, right? You need to understand what actually the difference between water drop and soap bubble, right? So do understand, this is a water drop So what is water drop? Here there is water and here there is air, right? If I am considering about the soap bubble, so bubble means what? So it will be having two surfaces. So the meaning of soap bubble is it is having two surfaces. So here there is water and here there is air and here is also there is air, right? So this is what now here? This is soap bubble. It is soap bubble. How many surfaces soap bubble has? Two surfaces. This is water drop which has a single surface, right? So this is water drop. It is water drop, right? Okay. Now if it has two surfaces, so what happens to the formula? The formula will be twice of this because it has two surfaces. The formula will be like this. So instead of T, we'll be having 2T. 2T into the bracket 1 by R1 plus 1 divided by R2. So 2T 1 by R1 plus 1 by R2. Right. So if it is single surface, pressure is T. Right. If it is having two surface, the pressure is 2T. 2T 1 by R1 plus 1 by R2. Right. So same side plus opposite side difference. If there are two surfaces, the formula changes into 2T now instead of T. Right. Okay. Now let us go ahead with another one case now here. Right. Let us go ahead with third case. Okay. The third case, let me take like this. For spherical surface having, see here, for spherical surface having one free surface. Okay, I am considering here spherical. Till now we consider different shapes now here. Here now I am considering about the spherical surface. For spherical surface having one free surface. Okay, one free surface. The example is what now here? Water drop. One free surface. Okay, if I am taking one free surface, what happens? Since it is spherical, right? If it is spherical, then the radius of curvature which I am considering R1 and R2, they will be equal. R1 and R2 will be equal to R, right? If it is spherical, do remember, spherical means radius will be the same, right? So that is the reason why we are considering R1, R2 equal to R. Then what happens to this formula now here, right? So P is equal to T, 1 divided by R plus 1 divided by R. So what happens now here? 1 divided by R plus 1 divided by R. So what do I get? This will be 2T divided by R. Okay, 1 by R plus 1 by R is 2 by R. Again 2T divided by R. Right. So this is the pressure inside a water drop, spherical surface having a single surface, free surface. Right. Okay. Let me take the same but with the two surfaces for spherical. See here. For spherical surface, again I am considering spherical. What is the meaning of spherical? Radii will be the same, right? Spherical surface having two free surfaces. Okay. So what is the example for two free surfaces? I told you already. The example is what we say here, soap bubble. Right. So what is the, since it is spherical, R1 equal to R2 equal to R. Then what happens to the excess pressure over here, right? So that happens, instead of T, what shall I take now here? 2T, right? Because it is having two free surfaces. 2T, 1 divided by R1 plus 1 divided by R2. So 1 by R plus 1 by R. So this is 2 by R. So how much do we get now here? 4T divided by R. Do you remember? If it is having two free surfaces for soap bubble, what is the excess pressure? 4T by R. You need to remember this because you will be having problems you need to solve based upon this now, right? For water drop, right? For liquid drop. So what is the pressure here? 2T by R. For soap bubble, it is 4T by R. Why 4T by R? Because it has two surfaces, right? Okay. This is the fourth case. Okay. Now, let us take another one case. Instead of spherical, let me take cylindrical. What happens now here, right? Okay. Let me go with case 5. Okay. What is case 5? Let us check it out now here, right? Case 5 for spherical surface. Now I will be taking for cylindrical surface. Okay, for cylindrical surface having one free space. Right? For cylindrical surface having one free surface. Right? Okay, that is we can take like this now here, right? Cylindrical column here, right? The example is you can take as soap bubble, that is cylindrical liquid column. cylindrical liquid column, right? So liquid surface, cylindrical liquid surface. Okay, if I'm saying, what is the specialty of cylindrical surface? Do you remember? Cylindrical surface, when we speak about cylindrical surface, one of the radii of curvature will be infinity. Since it's cylindrical, it will be straight, and radius of curvature of a straight line is infinity. So one of the radii of curvature will be infinity. If it is so, then which surface it is? Spherical surface, right? Okay. Now, if I am taking a spherical surface, right? So now what happens to the formula? Okay, let us check it out. P is equal to, what is the formula? T into the bracket 1 divided by R plus 1 divided by infinity, right? 1 divided by R, 1 divided by infinity. So what is 1 by infinity? 1 by infinity is 0 now here, right? So what do I get? So that will be T divided by R. Do you remember, this is for cylindrical surface, the excess pressure for cylindrical surface having one surface. Let us go with the last case, that is case number 6 now here, right? Okay, so what is case number 6? For cylindrical surface. For cylindrical surface having two free surfaces. If it is having two free surfaces, example, cylindrical bubble, we can create this kind of bubble, right? Cylindrical bubble. If it is a cylindrical bubble, then what will be the pressure, right? Again, so what gives cylindrical? So if I'm taking first radius of curvature as R, so second radius of curvature will be infinity. Then what happens to the pressure? Pressure, I told you, since it is having two free surfaces, so what happens now here? It will be 2T, right? So 2 into T bracket 1 divided by R plus 1 divided by infinity, right? If I'm considering this, so what happens to this now here, right? So it will be 2T divided by R here, right? So this is the case for a cylindrical surface, 2T by R. For a cylindrical surface having only one free surface, it is T by R. If it is having two free surfaces, it is 2T by R. So these are 6 cases about this pressure difference across a liquid surface. So today we derived the expression for pressure across a liquid surface, and we have considered all the 6 cases. So this is the end of the derivation and some cases about it.